Here's a quote from Noam Chomsky. "There is a notion of success which has developed in recent years which I think is novel in the history of science. It interprets success as approximating unanalyzed data." He's referring to the fundamental technique in machine learning, the idea of evaluation on a holdout dataset. Let's review what we've learnt about validation for probabilistic machine learning models. Here's a dataset, all the black points, and here's a holdout data point in red. Let's imagine this is a supervised learning problem, i.e. we want to fit a probability model for the y values parameterized by x. We might come up with a very crude model, for example a simple straight line linear regression. What I'm showing in this plot is the likelihood function over y evaluated at each x coordinate. This model is underfitting. It assigns fairly low likelihood to the dataset. We can see this because lots of the data points are in regions where the likelihood function is small. But at least the model has assigned an OK likelihood to the holdout data point. Or we could go to the other extreme. We could train an absolutely brilliant neural network to be a perfect fit for the training dataset, but then it may well assign hardly any likelihood to the holdout data point, so it'll score very badly in evaluation. What we're hoping for is a model that doesn't try too obsessively hard to fit the training data, but does make some attempt, because we believe that such a model will assign good likelihood to the holdout data points. So, in summary, we can evaluate our model by measuring the log likelihood it assigns to holdout data points. And here's the corresponding picture for unsupervised learning. Let's suppose we have an unlabeled dataset and we want to fit a generative model. We should keep a holdout dataset to one side and fit the model on the training data, and then just evaluate the log likelihood on the holdout data. If our model is underfitting, it will assign low likelihood to the holdout data points. If our model is overfitting, it will also assign low likelihood. So all we need to do is measure the log likelihood of holdout data points, and this will automatically measure if our model can generate novel values, but values that are nonetheless similar to those in the dataset. Okay, this is what Noam Chomsky is talking about when he says success is approximating unanalyzed data. But there's his other words, novel in the history of science. It doesn't mean novel as in new and exciting. It means novel as in new and misguided, a travesty of what science should be. Here's a picture to explain what he means. This is the machine learning mindset. The machine learning idea is that the job of a model is to generalize to new data. It's easy to test how well our model generalizes using holdout sets and measuring our model's log likelihood on those holdout data points. Typically, a machine learning person would shuffle their data and take, let's say, 20% at random to be the holdout dataset. That's what the sklearn library routines do, for example. Chomsky thinks that this is deeply misguided. Here's the scientist's way of looking at the world. The scientist wants to learn how the world works. They want to come up with theories that will work well in completely new scenarios, well beyond the dataset they used to invent the theory. Einstein's theory of relativity, for example, continues to be tested well after his death, using instruments and data well beyond what he knew about. A scientist would say, if your model only works on a random subset of your initial dataset, then it's a rubbish model. And so, generally speaking, they don't trust machine learning. They trust simple models based on understandable parameters and on well-grounded scientific concepts, because they trust that that sort of model will extrapolate well to completely new situations, and they don't trust that machine learning models will extrapolate well. Here's what scientists say about model simplicity. Everything should be made as simple as possible, but not simpler. And it's more important to have beauty in one's equations than to have them fit experiment. Actually, this isn't exactly what Einstein said. What he said is rather less simple. It can scarcely be denied that the supreme goal of all theory is to make the irreducible basic elements as simple and as few as possible without having to surrender the adequate representation of a single datum of experience. The devil is in the detail. What does he mean there by adequate representation? Anyway, I don't think it makes sense to be absolutist about this. We shouldn't expect our theories to apply to completely and utterly new scenarios that have nothing at all in common with our experience. It's reasonable to want our models to apply reasonably well to reasonably new data, but not completely off-the-wall new. What I'd recommend, though, to get just a little bit closer to the scientist's mindset is that you don't do the usual machine learning trick of taking a random subset of your data as holdout. Try to find a holdout set that's different from your training set. For example, take the most extreme 20% of your points, if you can find a way to measure extreme. That's the best way to make sure you're actually learning models that generalize. Let me finish by trying to summarize more formally what we're doing when we evaluate with holdout sets. Here's our generative modeling picture again. According to Einstein and Dirac and Chomsky, what we really care about is how well our model performs on data from new scenarios, not just a random shuffled holdout set, but genuinely new data. Let's call the new data x prime. We want models that work well on x prime. In other words, we care about the expected log likelihood that our model ascribes to new points drawn from x prime. But what we actually measure in machine learning is how well our model performs on the holdout dataset. A more formal way to write this is that we care about the expected log likelihood that our model ascribes to new points drawn from x hat, where x hat is the empirical distribution of the holdout dataset. So this is the real dogma of machine learning. It's the belief that we can approximate x prime by x hat. Machine learning isn't about model fitting, and it's not about neural networks. Model fitting is an ancient technique. Gauss did it back in the early 1800s when he invented linear regression, and neural networks are just slightly fancier model functions. No, what's new and groundbreaking about the way we do machine learning now is the idea of evaluation on holdout datasets. And the fundamental idea of a holdout dataset is that a finite sample of data points is a suitable stand-in for the unknown distribution of new data. Whenever you do any piece of machine learning validation, this is what you have to ask yourself. Do you believe the dogma? Do you believe it's appropriate for your problem? Have you chosen your holdout dataset in a way that will make the dogma appropriate?